All right, in this module, we're going to begin to pull all these variables we've talked about, the basics, and start discussing them as atmospheric circulations. What we're going to do first here is look at the global circulations. If we didn't have a rotating Earth, boy, it would be simple. We'd have basically warm air over the equator, rising, hitting the poles, sinking, getting colder, coming back down. Very simple. However, we have a rotation. And because of that, we have three separate individual cells that literally have formed because of that rotation. Yes, hottest temperature is still down the equator, coldest still at the pole. But because of the rotation, we have a global cells like these. So the Hadley cell generally develops over the tropics. What that means is there's sinking air. Notice it's going down right around 30 degrees north. Well, if you push air downwards, you develop high pressure. So you would expect high pressure along this latitude, right? Lower pressure down here by the equator. Up near 60 degrees north, we have another area of lift going up. So we would expect lower pressures around there. And finally, higher pressures at the poles, at the surface. And that's exactly what we start getting. You see this subtropical highs, low pressures. Because of that, we have here global circulations. We have high pressure that tends to be along 30 degrees north. We have low pressures that tend to be along 60 degrees north. However, we have seasons. So the actual global equator kind of moves north and south, following the sun. So in our winter time, it's further south, pushes these lows a little further south. They come across the mid-latitudes where we are more. High pressure that was originally at 30 degrees north kind of moves a little bit south. And the intertropical convergence zone, that low pressure that's right there by the equator, moves southward. And when they do that, it changes the flow of air across the globe. Notice India at this time in the wintertime. Winds are coming out of Siberian high. Well, looking up in Siberia, it's pretty dry, right? So you would expect a very dry circulation there. Now, let's go to summertime. All of a sudden, the intertropical convergence zones actually move to the north because of the heating of the equator there. And now the winds are coming out of the south. Lots of ocean down to the south. And they get plenty of rain. So you can see how these global circulations impact. And they impact high pressures over the ocean here. We have more of a high coming, our Bermuda high on the east coast of the United States. There's a Pacific high out there. The low pressures tend to move further up into northern Canada, across Greenland in the summertime. Now, if you're down in the south, obviously the seasons shift. So that's kind of a global circulation, and you can see it. The jet stream is going to be stronger in the summertime. I mean, it's going to be stronger in the wintertime, excuse me. And it's going to be down in the southern hemisphere. It'll be stronger in the wintertime in the southern hemisphere, which is our like July and June. And you can see here the jet stream. There's a subtropic where the sun generally keeps everything hot and humid. We have a jet stream right there at the edge of that, which is called the subtropical jet stream. Some days it really is prominent, and other days it's not. And we have a polar jet stream. All these jet streams occur because of temperature contrast. And the biggest temperature contrast are right at the top of the troposphere, right before the stratosphere, and at these junctions in the overall circulation patterns. So these are where the jet streams that tend to form are. And we'll look along here now. We're going to move into more from this. We're going to look at the atmosphere as a whole. And I wanted to just show you, start with a current weather map. So we got to understand what fronts mean in order to look at more the mid-latitude weather, smaller circulations. We looked at large-scale circulations a bit ago. Well, fronts define a difference in air masses. What do I mean by an air mass? An air mass tends to be a uniform body of air. So let's take up here in Canada right now. Air masses tend to form all the time up here in northern Canada. Why do they form there? Well, high pressure tends to sit there. High pressure means the winds are light. Winds are light means that the air is taking on the characteristics of what's under it. Well, what is under it is a cold snow field with very little radiation coming in from the sun at this time of year. So, as you can see here, minus 38, minus 47, minus 36, all extremely cold air, all the way even down here, minus 29s. This is a very cold Arctic air mass. It's over Canada. Separating it, out here, temperatures in the 40s, is a more, probably a maritime tropical air mass. What that means, tropical is just defining it's warmer than an Arctic or polar air mass. There also are maritime polar air masses as well, and it could be one of those as well. You have to look where it formed, because it probably formed over the northern Pacific. Maritime just means it's moist. Continental means it's dry. And right along here are the Rocky Mountains, or a series of mountain chains. So that is why it's stationary here. This Arctic cold air is very dense, and it's not getting over that mountain. It's low level. So you have a stationary front. Notice you have blue triangles, which indicate cold, warm semicircles, red semicircles, which indicate warm. So if I wanted to know whether a front is moving or not, look to see which side they're on. In this case, they're alternating, so it's a stationary front. Here, notice all the blue triangles are on this side. That front is a cold front moving this way. Here, all the semicircles are on this side. That is a warm front moving this way. Here, you have a semicircle and a triangle. What is that? That's an occluded front. Occluded front is really where a cold front, this cold front, has caught up to this warm front and pushed this warm air mass that was between the two aloft. So it doesn't show up at the surface anymore. That is where you're getting this occluded front. That happens near strong low pressure systems, which is what we have here. So the next step along this, well, if I know that a cold front is moving, also know that fronts have slopes. Remember, cold fronts slope back up to the main source of cold air. So this cold front is going to be at the ground here, but then it's going to get deeper and deeper, that cold air, as you go back this way. Warm air is going to actually be over top of this area where it's colder at the surface, but finally reaches the ground here. So each one of these has a slope, and let's take a look at that slope a minute. I'm taking you down to Florida. I know several of you are in Florida now, learning at flight schools down there. We had a cold front to go through Florida last evening. This is Tampa. It's an upper air sounding from Tampa. Here, the temperature is actually warming with height. So this is an area of cold air that has come in. It's about 1 kilometer thick. So if you were flying an aircraft today in Florida and got above what, 1,000, what, a little bit over a kilometer, a couple thousand feet up, you're changing air masses. You're literally moving. And you'll notice the wind direction where the air is colder is out of the north. Wind direction where the air is warmer is out of the west. Yes, the air temperature is beginning to cool again, as it normally does in the troposphere here. But this is the slope of the front. I wanted you to get a feel for that. Yeah, if it's a cold front, it's going to be a steeper slope. If it's a warm front, it's going to be a gentler slope. The steepness of that front indicates how fast the vertical motion can be. So if you have a very strong, fast-moving, very steep cold front, like we do sometimes, they're going to tend to push the air up very quickly. Then, if you have an unstable air mass, you probably get some pretty intense thunderstorms. And we're going to talk about thunderstorms more next week, next 2 weeks. I wanted you to look also back at a daily weather map. We had a pretty strong low earlier, 986 millibars here over the upper Midwest. Cold front went down to the south. Here you'll see that occluded front right there again, where it actually pushed the warm air aloft. Very intense low, right? And we know the pressure gradient, we just learned about winds, so there's a pretty strong northwest winds here. And maybe blowing down across the Great Lakes here. There's another low down here as well, taking shape. This low is going to become the predominant low. Sometimes you get wave trains. So this one is just now getting developed. Not really strong yet. But we're going to watch it develop over the next few days. We have the other one going out to sea. And here what I want you to look at is a jet stream. We have a deep trough of low pressure here at 500 millibars. And another one that came through with this one, kind of almost on top of the initial one right now. So you can see that right up here with the initial one. But this second one, let's see how it goes. Oh yeah, you notice you have a big high pressure sitting here. This is forming a jet stream that's going from southwest to northeast. Notice it's not penetrating too far to the southeast yet. Well, let's move to the next day. And this will be Thursday. Well, golly, that same low is now here. It's developing, gotten stronger. Oh yeah, notice the tilt. Back here we have a very strong upper level low yet. Lots of precipitation out ahead of it. So we're developing that low even stronger with time. And finally, we're going to move the next day on Friday. Now we're down over 1,000, about 1,000. Oh, there it is, 987 millibars. Same strength, a little further east, but same strength as the previous one we looked at. And notice that trough's beginning to weaken. This high pressure is part of a large scale. These large scale waves influence how these smaller troughs of low pressure develop. Here's another one coming into the west coast of the United States now. Right now, there's a large scale atmospheric high pressure aloft on the eastern part of the U.S. and over the western part of the Atlantic Ocean. That is forcing these cold fronts not to dip nearly as powerfully south as they might have. Yes, this one's going to come through Florida, but not nearly with the strength it would have had if that was a low there. So you can see how these have evolved. This whole pattern now, we're probably going to have an occluded front here very shortly. And you can see the Arctic air masses coming out behind these cold fronts. There's a very strong difference in temperature gradient across these. These are called extratropical lows. The book goes into tropical. Tropical systems form where there's no temperature contrast. They form basically in the tropics where fronts don't make it. They develop with time there. And because of that, they can get very intense And I wanted to just show you a quickie look at this. Because it shows you very nicely. Here is that cyclone, exactly the same pattern as I was just showing you that developed with that. And how that short wave developed in sync with it, influenced it because it created the divergence of loft that helped these to form. If you looked at a cloud view from satellite with this, you would be looking at a comma head. There, the cyclone. Now, tropical cyclones get very intense, and they form over the, like I say, the tropics. There is no temperature change. Just look at this. It's a circulation around Andrew. You can see very, very intense thunderstorms here. They're right here, very high tops. It is very different looking. It's circular. It's not comma shaped like an extratropical. And here you can see the eye has the lowest pressure, but has sinking air in it. The eye of an extratropical storm doesn't have sinking air in it. It has intense rising air. So that you wind up with the worst conditions right around the center. They're right on the center, literally, of an extratropical low. The worst conditions here are in the eye wall, which are outside the eye. Now, tropical systems, when they move out of the tropics, like a hurricane, may strike a cold front or a jet stream. When it does that, this tropical system will begin to transition, and it may become extratropical. Hurricane Sandy was one of the classics of this. It was a hurricane as it developed. As it moved up the east coast of the U.S., it became extratropical. Now, they generally weaken after a time after they become extratropical. They may be intense and shortly. But these are the kind of systems, when you're looking at the weather, as far as from a pilot's perspective, these are areas you better be taking and paying attention to. Along fronts, along lows, how they're going to evolve. Those are areas that are going to influence what weather hazards you have. So, hope you got a little bit out of this, and let me know if you have any questions.